Okay, we're going to work problem 5.32 from the end of chapter problems. This problem tells us about a sample of freon gas. It's freon 12. It gives you the formula. It occupies a volume of 25.5 liters at 298 Kelvin in this pressure, 153.3 kilopascals. What will this sample's volume be at STP? So a couple of different things about this particular problem. So this CFC12 or Freon 12 is an example of chlorofluorocarbon. And these are, of course, damaging to ozone in Earth's stratosphere. It can destroy the ozone catalytically. So these freon gases, this particular one, has been sort of phased out over time to protect the ozone. They've switched gases to different gases that are mainly just carbon and fluorine and maybe some hydrogen. It turns out those are a little bit better for the ozone hole. It's actually been a success story of atmospheric chemistry, as it turns out. So that's one sort of point of interest. Another thing is that we want to compare characteristics of this gas sample to values at something called STP. So if you don't know what STP corresponds to or what it means, it's called standard temperature and pressure, hence STP, standard temperature and pressure. Very specific set of conditions for temperature and pressure are required to meet this STP condition. That is 273 Kelvin, which is 0 Celsius. It's 273.15 to be more exact. And a pressure of exactly an atmosphere. If you meet these criteria for temperature and pressure, you are at STP. So this problem is telling us that we're holding this Freon 12 gas at non-standard conditions. And then we adjust them to standard conditions. We want to figure out what the volume is, okay? So I read this problem and I think kind of, again, initial and final type logic, right? And I see, well, what do I know about my initial? I know that my initial condition for volume is 25.5 liters. I know my initial temperature is 298 degrees Kelvin, given that in the problem. I also know an initial pressure. It's 153.3 kilopascals. I don't know anything else. Now, I look at this list of things I know, volume, temperature, and pressure. And pretty quickly, I realize that I've got most of the variables in my ideal gas equation. PV is equal to nRT. You say, well, it's like I'm missing 2, right? Well, remember, R is a constant. We use certain units of measure for the other terms. It's 0.0826. We'll see that here in a second when we get into this, okay? But if I plug in a constant value for R, there's really only one thing in this equation I don't know, and that's N, that's number of moles of my gas. So basically in the problem, I've been given all the information I need to figure out how many moles of gas must be present in this sample. And if I know how many moles of gas are present, I can really adjust for any conditions of volume, temperature, pressure. I can change it however I want and figure out, how the unknown variable changes. Okay, so that's sort of what we're going to do here for a strategy. Okay, as we get into this. So let's take a look then at sort of where we're at and where we need to go. So pressure, PV, right? Pressure times volume. Now, if I'm going to solve for N in moles, and I'm going to use R, the one that's given in your book, or the most common value. There's several given in your book, and there's several values for this, but the most common value for R is 0.082058. Now, the thing is that number, this 0.082, has very, very specific units of measure attached to it. So this R is 0.082. It has units of atmosphere liters per mole Kelvin. So what that means is that when you start plugging in numbers into the ideal gas law equation, if you use this constant for R, the units have to jive. So you got to use atmospheres for pressure. You got to use liters for volume. You got to use moles in Kelvin, okay? But you always got to use Kelvin anyway, and moles are just moles, right? But you got to use the right units is my message here. If you don't, you're going to get the wrong answer. Okay, now fortunately for volume, I was told that the initial volume was 25.5 liters, okay, up here. So my V units, they jive, right? Liters, I'm good. But my pressure units here in the problem are kilopascals. If I'm going to plug pressure into this equation, I need atmospheres. I need to convert. So that's the first thing I need to do here. So 153.3 kilopascals, K being the metric prefix. I need to multiply by a conversion factor that gets me to atmospheres, okay? And away from kilopascals, so those units are on the bottom, so they cancel. Now, let's see, what is that conversion factor? If I look it up in the book, it looks like there's 101.325 kilopascals per atmosphere. So if I do the math, I get 1.5129 atmospheres. I take that number, I put it right here, and my PV equals nRT, 1.5129 ATM. I multiply that by my volume in liters. Set that equal to N, where N is the number of moles, times R, my gas constant, times T, my Kelvin temperature. I'm told in the problem the original temperature is 298 Kelvin, or 0 degrees Celsius. So I have all the numbers that I need now to rearrange that equation and solve for N, where N, lowercase n, is my number of moles. If I do the math, I find I've got 1.5776 moles of my gas in this particular sample. Now, what am I going to do with this? Okay, well, I take that number of moles of the Freon 12 that I've got. I could convert that to grams if I want to, right? That's no problem. Just multiply by formula math. If I want grams of Freon 12, I don't want that here, though. I'm just going to take that amount that I've got, and I'm going to compress it, expand the volume, change the temperature, whatever I need to do to achieve this STP condition, okay? This STP condition is sort of my final case. Now, what do I know about that? Well, I know, by definition, temperature at standard conditions is 273. And I know, by definition, pressure at STP is 1 atmosphere, okay? So if I go back to my PV equals nRT equation, there's some things that I already know. For instance, P is 1. It's 1 atmosphere. Now, in this problem, I believe I'm trying to figure out what the sample volume is at this condition. So that's going to be my unknown. So 1 times V, 1 times anything is just that variable. So V is equal to nRT for my purposes here in this particular problem, right? Now I know that the number of moles of my gas hasn't changed. None has leaked out or anything. It's just, I still got this 1.5776 mole. So I'm going to plug that in for my N. My R is always that 0.082 number that we talked about earlier. As long as the units are in atmospheres for pressure and liters for volume, that's good. So I'm going to plug in my R, and then I still have to multiply that by my T. Now I'm running out of space here. I guess I should maybe just rewrite it down here for clarity. So 1.5776, I got to multiply it by my R, the 0.082 number, that's my gas constant, right? And then I got to multiply that by my T, which is my temperature at STP, which is 273. So plug that all in, plug and chug. I do the math on that, and I find my volume under this condition is 38.577 liters, okay? So my final volume is a little over 38.5. My initial volume was 25.5. So it looks like my gas sample has been allowed to expand some. We went from 25 to 38 something, right? Between initial and final condition, the temperatures remain the same. So what other variable changed? Well, it looks to me like maybe the pressure changed. In the more compressed case, where my volume was smaller, note that the pressure was about 1.5 atmospheres. But what I did is I increased that volume to get to STP, because STP specifies 1 atmosphere. So the pressure was lowered and the volume correspondingly increased with the other things remaining constant. Okay? So this is a nice example where we used the ideal gas law, PV is equal to nRT, to solve one of these problems, sort of in a before and after sense. And sort of an added bonus or an add-on to this problem is that to solve it, you had to understand what STP was all about. Okay, so that's another reason why they ask you, what the STP condition was all about. So you have to remember what that is.